start a new chapter which is related to motion. When do we say that a particle is in motion? Whenever there is a change in the position of the particle, we say that the particle is in motion. We also use the term with respect to the surrounding. Why this term? Suppose, for example, you are sitting in the train. You are stationary, but still I say that you are in motion. Why? How can it be possible? You must be thinking that. It is possible with respect to the observer who is observing you from outside the train. So that means with respect to the observer observing the person inside the moving train, the person is stationary, the person is moving, but with respect to the train, the person is stationary. So this is the difference. So whenever we talk about position, we always have to mention the term with respect to the surrounding. So the change in the position of the object with respect to the surrounding is known as motion. Now related to motion, some scientists observe that whenever the particle or an object is set in motion, there was some or the other force acting on it. So some of the scientists such as Einstein defined that motion, that force, as the push or pull that is applied to a body to change the position of the object is called as force. The term force was then further clarified by Newton by giving certain statements related to force. We will go through in the next section. But for example, a book is kept on a table. It will be stationary unless and until it was acted upon by another force or it was lifted by somebody. So force is also distinguished as balanced and unbalanced force. For example, if a block kept on a table, the block will remain on the table unless it is acted upon by the other force, but the block is applying some amount of force on the table such that it is not moving. And in reaction, the table is also applying the equal amount of force on the block, which keeps it stationary on the table. So the force which keeps a body stationary on the surface is called as balanced forces, whereas the forces which help the body to move, either to change the position or to bring the object back to the original position, such forces are unbalanced forces. This statement was given by Newton. The statement was, any body which is at rest, it continues to stay in the state of rest, or a body which is in motion, it continues to stay in the state of motion unless and until it is acted upon by an unbalanced force. Now, Newton described two quantities, that is inertia and force. Force is that quantity which is required to change the position of the object from the initial position or to bring it back to the original position. Whereas inertia, he defined inertia of a body as the tendency of a body to remain in the state of rest or in the state of motion if it is in the state of motion in the same direction. So we can define the term inertia as the inherent property of a body by the virtue of which it can remain in the state of rest if it is at rest, or it can be in the same position of or in motion if it is in motion. So inertia of a body depends on mass. We can also say that inertia is the quantity which describes mass, or it is the quantity to measure mass. Inertia can be of three types: inertia of rest, inertia of motion, and inertia of direction. Now what is inertia of motion? By definition, we can say it is an inherent property of the body by the virtue of which the body stays or continues to stay at in the state of rest. For example, we can explain that with the help of examples. First example we can take, while dusting a carpet. When we have to dust a carpet, we just move the carpet upside down. What happens exactly in that case? We are moving the carpet, at the same time the dust particles which are stuck to the carpet, they remain in the state of rest because of the inertia into it. So those particles of dust which remain in the state of rest remain at the same position, whereas when we move the carpet, they get detached from the carpet and they fall down. This is the way how inertia of rest works. The second example that we can see is in case of a star, in case of a bus. When we are standing in the bus, we are in the state of rest. Even the bus is in the state of rest. When at the same time, when this bus starts suddenly, what happens? When the bus starts suddenly, our body will experience a jerk. Because of that, why it happens, why that jerk is happening? Because our body which is at rest continues to stay in the state of rest. Whereas when the bus starts moving, the lower part of the body starts moving along with the bus. And the upper part of the body still is in the state of rest. Because of which we experiences a backward jerk, and even sometimes we may fall if it is at very high speed. Another example we can use in the gardens, while we are plucking or we are removing fruits from the tree. What we exactly do? We shake the branches. What happens due to that? When we shake the branches, the trees, because of the inertia into it, they remain in the state of rest while the branches are moving. Because of that, the trees, the fruits gets detached from the branches and they fall down. This is how inertia of rest works. The second property is inertia of motion. Now how it works? Inertia of motion. What is inertia of motion? It is the inherent property by the virtue of which a body continues to stay in the state of rest. How can we explain that? A body which is in motion, it continues to stay in the state of motion unless and until it is acted upon by another force. So that property of the body to stay in the state of motion is called as inertia. How do we explain that? With the help of examples. First example, we can say, whenever we are, suppose we are standing in a moving bus. The bus is moving. When the driver applies a sudden brake to the bus to stop, what happens? Because of the moving bus, our complete body was in the state of motion. But as soon as the brakes are applied, the bus stops, because of which the lower part of the body comes to rest while the upper part is still in motion. Because of the whole situation, our body experiences a jerk. This is how a person may fall in the moving bus when sudden brakes are applied. Another example we can say, the rotation of fan. When the fan is switched off, it still continues to rotate till some time. This happens because of the inertia of motion of the fan. It continues to rotate. Third example, a person falls from the a person may fall from the train when he tries to jump out of the moving train. Now, why this thing happens? Whenever a person is in the moving train, he is also in the state of motion along with the train. When he tries to jump off, he tries to land on the stationary ground. As soon as the legs which are in motion along with the train lands on the stationary ground, it gets changed, it gets converted into the state of rest, because of which the person may fall. Next is inertia of direction. Inertia of direction is the inherent property by the virtue of which a person or an object continues to stay in the same direction unless and until it is acted upon by an external unbalanced force. The example that we can see to understand what it means is, very first, whenever we are riding a car or bike, the mud that is getting stuck to the tires, because of the rotation motion of the tire, the mud gets moves out of the tire in the tangential way. This is the change in the direction because of the force, circular force. Another example we can say, the sharpening of knife. Due to the circular motion of the wheel of the sharpener of the knife, we can see some spark coming out in the tangential way. That spark is due to the change in the direction due to circular motion of the wheel. This is how we can explain inertia. Inertia, we explained 3 types of inertia, which was inertia of rest, inertia of motion, and inertia of direction. So inertia of motion, it helps a body to continue to stay in the state of rest. Inertia of motion, it helps a body to continue in the state of motion, whereas inertia of direction means it is the tendency of a body to continue in the same direction. These definitions were given by Mr. Isaac Newton, and he very beautifully designed or stated the law, his first law of motion, which we call as Newton's first law of motion. He stated that a body continues to stay in the state of rest if it is in rest, or it continues to stay in the state of motion if it is in motion in the same direction unless and until it is acted upon by an external unbalanced force. Now, if we talk about force, we can describe force with the 2 things, that is, first is magnitude as well as the direction. So we can say force is a vector quantity. Similarly, in the second law of Newton that he gave, it consists of some force part and a new quantity which is known as momentum. Now force, whenever force comes in picture, we think about mass and velocity. Mass and velocity of an object can change the motion of an object. So momentum, he defined momentum as a body with velocity. A mass with velocity is equal to momentum. Mathematically, we can define it as, it is the product of mass and velocity. We denote it with P, momentum, as P, and we write it as M multiplied by V. Newton then explained his third law. In the third law, he gave the reaction and action between the force and the interactive bodies. In this law, he stated that for every action there is an equal and opposite direction, which means whenever an action is done, it has some or the other reaction in the opposite direction. For example, we can say forces never appear singly, they always appear in a pair. For example, if we strike a ball with a bat, we apply some amount of force on the ball using the bat. Same amount of force will be applied by the ball on the bat, because of which the cricketer may experience a jerk in the hand. In the same way, we can also see another example while shooting with a gun. While shooting with a gun, a force is applied to the bullet so that it goes in the further direction. The same amount of force the bullet also applies on the gun, because of which the shooter experiences a jerk in his hand and the gun moves back. The third example that we can see is a rocket. Whenever we have to launch a rocket in the upward direction, the down portion of the rocket, which consists of fuel, is ignited. because of the chemical reaction in the bottom part of the rocket, it gets ignited, and because of that it moves in the upward direction with a great force. These were the three examples to explain the third law given by Newton, which states that for every action there is an equal and opposite reaction. Now further we can talk about principle of conservation of momentum. Now what do you mean by the term conservation? Conservation means something which cannot be destroyed, neither it can be made or neither it can be made. The amount or the quantity remains same everywhere. So when we talk about momentum, conservation of momentum, we are talking about that we are saying that momentum cannot be destroyed, and the amount of mass and the force applied and the velocity with which it is moving remains the same everywhere. If we consider two bodies, two moving bodies, if suppose two moving particles collide with each other, the momentum of the two bodies before collision will be equal to the momentum of the two bodies after collision. Another example we can say, why do you think an athlete before taking a high jump first start running, and why can't he take a jump directly without running? He always starts running first and then he takes a jump. Why does it happen? Which of the three laws of Newton is applied in this? I can help you with that. Actually, the third law, that is the action and reaction. Because in a high jump, an athlete always takes a run before jumping. Why does he do that? And why do you think which law of Newton applies here? With the help of which law does the athlete does this? This is because of both the laws, second and third. As the second law states that a body continues to stay in the state of rest and in the state of motion if it is in motion, unless and until it is acted upon by an external force. Whenever an athlete has to jump, it has to put a lot of force on his legs. If suppose he doesn't run and he jumps directly, that means his legs are at the state of rest. And when it jumps, it suddenly starts in the state of motion. When it comes back, because of the third law of motion, that is every action has equal and opposite reaction, because of the reaction of the ground, the athlete may injure his leg. Because of that, the athlete has to run and set his body, his legs in motion before taking a long jump, just to avoid the injuries. So this is how the laws of Newton, the laws of motion given by Newton, help us in the day-to-day life. Now another example we can say, you tell me which of the following will have more inertia into it? A rubber ball or a stone? If both are of the same size, which of them will have more inertia? A stone will have more inertia. Why? Because inertia of a body depends on the mass of the body. More the mass of the body, more will be the inertia. Another example to explain is we can take a train or a bicycle. A train has more inertia than a bicycle. Now tell me friends, why do you think we are suggested to tie up our luggages if we are keeping it on the roof of the train? It is because of the second law of inertia, second law of motion, which states that because of that second law of motion, the luggage may fall down because it is in motion with the train. If the train stops, the luggage may fall down. So in this way, the laws of motion can be helpful to us in many ways in the life. Let us continue with the explanation of second law of motion given by Newton. We can say that rate of change of momentum is directly proportional to the impressed force and it takes place in the direction of the force. Mathematically, we can write it as the rate of change of momentum, which is change of momentum with respect to time. Suppose m is the mass of the object, v is the final velocity, and u is the initial velocity. Therefore, m in common, v minus u divided by t. Now here, v minus u by t is equal to acceleration. As per the definition, we can say that the rate of change of momentum is directly proportional to the force. The unit of measurement of force is Newton. 1 Newton is equal to the force applied to move 1 kilogram with an acceleration of 1 meter per second square. So 1 Newton is equal to 1 kg per centimeter or meter per second square. So this is the definition of 1 Newton. 1 Newton is also equal to 10 raised to 5 dynes, where Newton is the SI unit of force and dyne is the CGS unit of measurement of force. Now, to understand the concept of conservation of momentum, we consider two bodies of mass m1 and m2. Suppose m1 and m2 moving with velocities u1 and u2. Both the masses collide to each other with the force. Suppose the mass m1, suppose A, has the force F1 and it collides B with force F2. Then it will be given as F1 equals to minus F2. Because of the third law of conservation, every action has equal and opposite reaction. We use a negative sign. F1 is equal to minus F2. M1A is equal to M2A2. Splitting this, we get M1 V1 minus V2 upon T equals to M2 V2 minus U2 upon T. So M1 V1 minus U1 equals to M2 V2 minus U2. This becomes M1 V1 minus M1 U1 equals to M2 V2 minus M2 U2. M1 V1 minus M2 V2 equals to M1 U1 minus M2 U2. From this statement we can state that final momentum is equal to the initial momentum. Hence, with this we can state that momentum is conserved. So let us just see some numericals related to the topic. The first question that we have: calculate the acceleration produced when the force of 350 Newton acts on the body of 500 grams. So how to do that? First we will note down the given data whichever we have. We have mass 500 grams and we have force 350 Newton. We have to find the acceleration, so we will use the formula of force, which is equal to mass into acceleration. Substituting the values, 350 is equal to 500 into A. A will be equal to 350 divided by 500. We get the acceleration of 0.7 meter per second. So proceeding with the next sum, we have to calculate the momentum of the gun, which has the mass 500 kg and it recoils after getting fired with a velocity of 0.25 meter per second. So first we will write the given data where mass is equal to 500 kg and velocity is 0.25 meter per second. We have to find momentum. So the formula for momentum is mv, where m is the mass and v is the velocity. Substituting the values, 500 multiplied by 0.25, we get momentum is equal to 125 kg meter per second. So this is the answer we have found. For a gun of mass 500 kg which recoils with a speed of 0.25 meter per second, the momentum will be 125 kg meter per second. So our third question is, we have a railway wagon which is moving. The railway wagon is having mass 2500 and it is moving with a speed of 36 km per hour. It collides with a stationary wagon which is of mass 3000 kg. When after collision, if it moves with the same velocity, we have to calculate the common velocities. So we will first note down the given data. M1, which is the mass of the moving wagon, is 2500 kg. M2, mass of the stationary wagon, is 3000 kgs. U1, which is the velocity of the moving wagon, is 36 km per hour. We'll just convert it into meter per second. So 36 multiplied by 1000 divided by 60 into 60. We get 10 meter per second. U2 is the velocity of the stationary wagon, which is 0 because it is stationary. Now we apply the formula, which is we have to find the final velocity of the both, that is V1 and V2, which will be the same. So we have to find V1, which is equal to V2. So we take it as V. So M1 V1 minus M2 M1 V1 minus M2 U2 equals to M1 V1 minus M2 V2. Here, substituting the values, we get 2500 multiplied by 10 minus 3000 multiplied by 0 equals to again 2500 V minus 3000 V. 25,000 minus 0, and this side will be getting V as common. 2500 minus 3000. So the formula that we are using is M1 U1 plus M1 U2 equals to M1 V plus M2 V. Here V is the final velocities. Substituting the values, 2500 into 10 plus 3000 into 0 equals to 2500 V plus 3000 V. Here we get 25,000 equals to 5,500 V. Therefore, V will be equal to 25,000 divided by 5,500. 0, 0, 0, 5, 11, 5 5s are 0, 11 1s are 11 4s are point, 11 5s are 11 5s are. So velocity that we are getting is 4.55 meter per second. This is the final velocity with which both the wagons start moving together. The fourth question is, there are two balls of masses 50 grams and 100 grams. They are moving along the same line, and if they collide, the initial velocities of the two balls is 3 meter per second and 1.5 meter per second. After collision, the first ball starts moving with a velocity of 2.5 meters per second, and we have to calculate the velocity of the second ball. So to calculate that, we will first write the given data and do the following conversions. Mass of the first ball, that is M1, is 50 grams. We will just convert it into kg, so it will be 0.05 kg. M2, which is 100 grams, will be 0.1 kg. kg. Now u1 is equal to 3 meter per second and u2 is equal to 1.5 meter per second. v1 is 2.5 meter per second. v2 we don't know and we have to find that. So to find the velocity, we use the same formula that we used previously, m1 u1 minus m2 u2 plus m1 v1 plus m2 v2. Now we substitute the values. 0.05 into 3 plus 0.1 into 1.5 will be equal to 0.05 multiplied by 2.5 plus 0.1 multiplied by v2, which is unknown. So this will become 0.15 plus 0.15 again, which is equal to 0.5 into 25, 0.125 plus 0.1 into v2. So v2 will be equal to, we just add these both, so it will be 0.5 plus 5, 10, 2, 3 divide by minus 0.125, the whole divided by 0.1. So v2 is equal to 0.2. If we do the calculation, 0.125 5820 divide by 0.1, v2 will be 0.0285 meter per second. This is the final velocity of the second ball. So we do the calculations. v2 is equal to 0.300 minus 0.125. We get 5, 7, 1. So the answer is 0.175 divided by 0.1. So v2 is 1.75 meter per second. This is the velocity with which the second ball starts moving. So this was all about Newton's laws of motion, and we covered all the 3 laws of motion with the numericals. Thank you for watching Study Spectrum. Goodbye.